Hi, my name is Leonie Becker.
And my name is Nilsson, and together we will be presenting this paper on behalf of our team of students and researchers, representing the European Space Agency, the German Aerospace Center, as well as a number of academic institutions from across Europe. 50 years after Apollo, humanity is now on the verge of going back to the moon. The NASA-led Artemis program aims to send astronauts to the lunar surface by 2025 and establish permanent bases on the moon by the end of this decade. Unlike the Apollo moon landings from half a century ago, Artemis is targeting the south polar region of the moon, where frozen water is believed to be preserved at the bottom of permanently shadowed craters. The low sun angles in the south polar region results in challenging lighting conditions, with much of the environment being shrouded in long pitch-black shadows. A new generation of lunar systems will have to be built for this particular purpose, carefully designed to operate safely and reliably while facing these extreme environmental conditions. Design of solutions for the moon is typically guided by prototype deployments in so-called analog environments that share some of the environmental properties of the moon. Studies have, for example, been conducted on the ocean floor to simulate reduced gravity, or in dark underground caves to approximate the challenging lighting conditions. Unfortunately, these analog studies are a logistical nightmare and have been criticized for being resource-intensive and notoriously incurring budget overruns and project delays. A major underlying reason is that analog design studies are characterized by a small number of experimental deployments taking place relatively late in the project lifecycle and typically only involving a small number of participants. This leads to slow feedback loops that are antithetical to traditional user-centered design approaches, which have seen so much success in HCI. But as my colleague will elaborate, there might be a better way.
In this paper, we set out to explore whether virtual reality could be used to tackle some of these challenges. VR has the capacity to interactively simulate hypothetical concepts and environments at comparatively low costs, which has proved useful in supporting design activities in numerous other domains, ranging from architectural visualizations to planning of fire evacuation procedures. However, when it comes to design of solutions for human exploration of the moon, VR remains largely underexplored. To assess VR's potential use in this unique context, we had to start out by creating a realistic lunar virtual environment. Based on topographic scans of the moon acquired by the Lunar Reconnaissance Orbiter, we virtually reconstructed 64 square kilometers of landscape in the lunar South Pole region. We also paid great attention to faithfully recreating the unique lighting conditions on the lunar South Pole with blinding highlights and long-pitched black shadows. This virtual moonscape then formed a figurative sandbox in which we could simulate any hypothetical lunar surface scenario. In our case, we simulated a cargo unloading scenario centered around a European Large Logistics Lander. The European Large Logistics Lander, simply known as ER3, is an autonomous lunar landing vehicle currently under development by the European Space Agency. Its main purpose will be to carry out cargo delivery missions in support of future lunar ground crews. This makes the ER3 into a representative example of a future lunar surface solution and a fitting target of our study. Specifically, we recruited 20 participants to help us evaluate the scenario. Each participant was asked to approach the lander, to retrieve a cargo container and transport it to a nearby drop-off point. A semi-structured interview was then conducted, in which the participants were asked to reflect on various aspects of the lunar lander. The participants were all hand-picked human spaceflight experts and included active astronauts, aerospace engineers, astronaut instructors, managers, and scientists. Unsurprisingly, the reflections made by our participants were largely concerned with the lighting conditions. Strategies for dealing with the deep lunar shadows or the ideal position and intensity of artificial lights were frequently discussed. Participants also reflected on ergonomics aspects of the lander itself and accompanying lunar equipment. Container handles, for instance, were seen as too small. The angle of the ladder was criticized for increasing the risk of astronauts damaging the solar panels while climbing up the lander. While VR proved useful in eliciting numerous actionable reflections, we also came across instances where it appeared lacking. The absence of haptic feedback was specifically brought up, with participants stating this impedes their ability to estimate inertia and mass of objects. The inability of VR to properly simulate suit constraints was likewise brought up as a significant limitation.
At the beginning of this paper, we criticized analog field studies and prototype deployments for being inefficient and unable to fully facilitate user-centered design approaches. To explore an alternative approach, we have carried out a simulated field study in virtual reality. Our findings have demonstrated that conducting such simulated field studies is indeed feasible and comes with a number of potential benefits. Here we summarize these benefits into 3 main takeaways. The most obvious advantage is that VR can visually simulate some of the challenging lunar conditions inside a lab, which saves time and resources. Although VR has its problems, such as the limited haptic feedback, this is countered by its unique ability to accurately recreate the lunar lighting situation. Given the crucial role that lighting will play in future lunar missions, this makes VR into a highly useful tool for early ideation and design planning of lunar surface solutions. In this sense, VR effectively becomes a vehicle for enabling user-centered design methods in this otherwise engineering-dominated field. Unlike most other prototyping tools, by simulating scenarios in virtual reality, both design concepts as well as their operational context are being conveyed simultaneously and made available for evaluation. This is important because the success of future lunar expeditions will depend on efficient interoperability within complex human-machine ecosystems involving people, hardware, and software solutions. VR-based scenarios put the spotlight on such interoperability and in the process highlight important synergies and frictions. Finally, by enabling user-centered design, VR introduces agile elements into otherwise rigid project structures. In addition to simply enabling user studies, VR conveys detailed models of intended project outcomes, making these available for review by relevant stakeholders in a concurrent manner. As demonstrated by our work, VR is a viable tool for engaging diverse stakeholders, ranging from astronauts to engineers, from managers to scientists, providing a unifying language that makes early-stage design solutions, their co-creation and assessment accessible across fields and disciplines. In conclusion, our paper demonstrates that emerging technologies such as virtual reality, in combination with established user-centered design methods, and more broadly HCI as a whole, are well positioned to play a leading role in tackling many of the challenges that surround humanity's expansion to the moon and beyond. Thank you.